Hi guys. We're going to be looking now at question 4 from the 2015 paper 1 exam. Alright, so we have complex numbers z1, z2, and z3 such that 2 over z1 equals 1 over z2 plus 1 over z3. And z2 equals 2 plus 3i and z3 equals 3 minus 2i, where I squared equals minus 1. Write z1 in the form a plus bi, where a and b are integers. Okay, so how are we going to go about this? Well, first let's try and identify what's important. So we have this relationship here. We have what z2 and z3 are, and we want to write z1 in the form a plus bi, a and b integers. Alright, so what is the question giving us? Alright, so it's giving us a relationship 2 over z1 plus, equals 1 over z2 plus 1 over z3, where z2 equals 2 plus 3i and z3 equals 3 minus 2i. Okay, so are there any relevant formulas? It doesn't look like it. So let's just write out our equation. So we're going to be solving for z1 equals 1 over 2 plus 3i, because that's what z2 is, plus 1 over 3 minus 2i. Okay, so whenever we have a complex number sort of fraction where we have 1 over a complex number, or we have a complex number on the denominator, the way that you deal with that is you multiply the top and the bottom of the fraction by the conjugate of the denominator. So that sounds very confusing. What does that mean? Alright, so let's look at this part. 1 over 2 plus 3i. Now that's very ugly, not fun to work with. So let's just work with that for a second. So actually, let's just work over here. So 1 over 2 plus 3i is the same as 1 over 2 plus 3i multiplied by 2 minus 3i over 2 minus 3i. And of course it is, because 2 minus 3i over 2 minus 3i is 1. So we're basically just saying 1 over 2 plus 3i is the same as 1 over 2 plus 3i by 1. So now if we multiply top by top and bottom by bottom, we get 2 minus 3i all over, if we multiply bottom by bottom, we get 4, bracket by bracket, 3i by 2 is 6i, minus 2 by 3i, minus 6i, and then 3i by minus 3i is minus 9i squared. So this equals 2 minus 3i, and this might not seem like an improvement yet, but the bottom will clear up nicely. And then the 6i and the minus 6i will cancel, and I squared is minus 1, so we can just put minus 1 in place of I squared. So then we get 4 plus 9, or let's just write that as 13. Okay, so we have an expression for 1 over z2, 2 minus 3i over 13. And now let's try and get an expression for z3. So 1 over 3 minus 2i equals, same thing, 1 over 3 minus 2i by, remember, conjugate over the conjugate. So 3 plus 2i over 3 plus 2i. And so now if we again multiply top by top and bottom by bottom, we get 3 plus 2i over 9 minus 6i plus 6i minus 4i squared, which is just plus 4. And this equals 3 plus 2i over 13. So now this is actually cleaned up quite nicely, because they're both over 13, so we can just add them like normal fractions. So now we get that 2 over z1 is equal to 2 minus 3i over 13 plus 3 plus 2i over 13. So it's over the same number, so we can just add these together, and we add real plus real and imaginary plus imaginary, so we get 5 minus I over 13. And that's equal to 2 over z1. So now we'll see if we cross multiply, we get 5 minus I by z1 is equal to 26. So now we can just divide by 5 minus I on both sides, and we get z1 is equal to 26 over 5 minus I. And now we can do the same sort of thing, where we the same sort of thing as we've just done to write 26 over 5 minus I. So 26 over 5 minus I is equal to 26 over 5 minus I, and multiply by the conjugate top and bottom. So 5 plus I, this is just always our trick. If you ever have a fraction with a complex number on the bottom, always multiply by the conjugate over the conjugate. Just makes your life much easier. 5 plus I. Okay, so what does this equal? So 26 by 5 plus I would be 130 plus 26i all over 25 minus 5i plus 5i minus I squared, and that's just equal to minus 1, which is just plus 1. And that equals to 130 plus 26i over 26. And this works very nicely now, because 130 divides into 26 as does 26. So we can just write this, z1 equals 126 into 130 is 5, and 26i is I plus I. So how does it ask us to write the thing? It asks us to write a plus bi, so I suppose we would just write this 5 plus 1i, although it doesn't make any difference. And that would be our answer. Z1 equals 5 plus 1i. So let's put that into our box. 5 plus 1i. Alright, so now we're on to part B of this question. Let omega be a complex number such that omega to the n is 1, and omega does not equal 1, and s equals 1 plus omega squared plus ... omega to the n minus 1. Use the formula for the sum of a finite geometric series to write the value of s in its simplest form. Okay, so first things first. What is the information giving us? So we know that omega to the n is 1. Omega does not equal 1. And s, our sum, is 1 plus omega squared plus omega to the n minus 1. Okay, so it then mentions a finite geometric series. Okay, so straight away, what's our formula for a finite geometric series? Okay, so our formula for a finite geometric series, so a series of the form a plus ar plus ar squared plus ... ar n minus 1. Now remember, it's still arn minus 1 because this means that there's n terms. So Sn will be a sum of n terms. It might be a little bit confusing. And so the formula for this is Sn equals a to the 1 minus rn all over 1 minus r. Okay, so let's just plug this in. So what is a? So in our case, a is 1 and r is omega. So let's just plug this in. S equals 1 times 1 minus omega to the n all over 1 minus omega. And now, what do we know? Well, we know that omega to the n is 1, so we can just sub that in. So we have 1 times 1 minus 1 over 1 minus omega. So this is 0 over 1 minus omega. So, of course, that's just 0. Now, the reason that they include that omega does not equal 1 is because if omega did equal 1, then we would have a 0. We would have a 0 here. So then we'd have 0 over 0, and that's indeterminate. So that's just a safeguard so that you don't get any weird things like that. And so that's just it in its simplest form. So let's just write that. So S equals 0.